So what we discussed, of course, is that in addition to the fact that a changing magnetic field drives a curling electric field, a changing electric field drives a curling magnetic field. And we also discussed the fact that there are approximations that are often made, especially if we're thinking about, for example, electronic circuits with AC currents and things like that, where we ignore the interplay between changing fields driving curling fields. For example, quite often we will make the approximation that we will include the Faraday effect but ignore the displacement current. And we discussed how that is a good approximation if the characteristic size of our circuit is small compared to the time it takes light to propagate across that circuit. That's the so-called quasi-static regime. Ultimately, if we're far enough away from wherever the sources are, such that C times that time is equal to L, well then that's no longer appropriate to neglect either one of these terms. We must include both. And we know that that is the regime in which electromagnetic waves are important. So even if our particles are moving, or charges are moving at non-relativistic speeds, we still have the displacement current, and that shows up in terms of electromagnetic radiation. Okay? So, of course, we'll spend the latter half of the semester talking about waves and radiation. One of the things, though, that follows now that we have, this is it, we're done. We have Maxwell's equations. Now it's just a matter of the implications thereof. We discussed some aspects that we can derive, in particular where we talked about the conservation of energy, of electromagnetic energy, and how that follows from Maxwell's equations and the Lorentz force law. So to remind you what we were talking about, a general form of a conservation law has this kind of continuity equation whereby we look at some volume and we ask about there's some stuff inside that volume which could be floating around and it could be being created and destroyed inside that volume. Boy, this is the most abstract picture you've ever seen, whatever the hell that means. But the point here is that there's stuff inside that volume, it's flowing around and could be popping into existence or being absorbed somehow. And we capture that concept mathematically in terms of a continuity equation, which says that the amount of stuff inside this volume is changing as a function of time because either it's flowing into or out of the volume, or it's being absorbed or emitted. Means it's locally being created. And if R is negative, destroyed. In the case of charge, there was no such term like this. We just had, there was no creation or annihilation of charge, and we said charge was just, only reason the local charge would change was due to flow, but not due to transferring charge into some other form of stuff. So the quantities of interest here, the amount of stuff, we have a local density of that stuff, we have a flow of that stuff, and we have the creation rate of that stuff per unit volume. So, in particular, we were talking about, at a last class, we were talking about deriving the conservation of energy law in electromagnetism. And so, energy can in electromagnetism can kind of reside in two forms. It can reside in the fields or in the kinetic energy of the charges. Okay? So the mechanical energy of the charges can change due to work done upon them by the fields. Or vice versa, the negative of the work done on the charges is the energy that's going into the field. So if the charges are losing energy, the only place that's going in this case is, well, it could be heat or a field. That's where it could be residing. And so what we showed, of course, is that the rate at which the fields do work on the charge was related to this. So the negative of that is the rate at which this is increasing. So using Maxwell's equations, relating J to the local curl of B and the time derivative of E, and plugging that back into this expression, we arrive at Poynting's theorem. So Poynting's theorem tells us that the stuff is energy in the field. And that is equal to the integral of the local energy density. So that plays the role of rho. And the energy density is E squared plus B squared over H pi. And the Poynting theorem tells us that the rate of change, oh, I should say perhaps, before I do that, that the integral form is here, but the differential form of this follows from Gauss's law. And so we have, in this case, minus del dot S plus the rate of creation is minus d dot. Or often written. Like this. Where S is the Poynting vector. S is equal to E cross B plus U times C. Okay? So, the Poynting vector represents the flux density of electromagnetic energy. This is, as we said, for a general conservation law, we're talking about the rate at which electromagnetic energy flows per unit area. So it has units of power per unit area. And if electromagnetic energy changes locally, it's either because it's flowing or that energy is doing work on charges. Or the charges are doing work on the fields, right? So if J dot E is positive, then minus J dot E is negative, which means that energy is being dissipated. If J dot E is negative, then this is positive, then electromagnetic energy is being created. And we looked at two examples. We looked at the dissipation example, thinking about ohmic heating as charges are colliding with defects and causing resistance, and that then goes into heat, and that electromagnetic energy then is dissipated. Of course, if we have a steady state circuit, there's a source of energy which is coming from the power supply, which would make detailed balance ultimately. And we also looked at another example where we looked at the charging up of a capacitor, and when we charge up the capacitor, we create energy in the electric field, and the way we just sort of did a thought experiment there is where we move charges counter to the existing field, and the work that was done in order to do that must go into the electromagnetic energy, or in this case, the electric energy, electrostatic energy stored in the capacitor. All right? Anybody have any questions about any of that? All right. So, now, we've talked about energy, let's talk about momentum. So, the rate of change of mechanical momentum of the charges is equal to the force on the charges, right? Which is, in this case, well, if I have a general distribution, I have the Lorentz force law here written for a general distribution of current and charge, right? That's the Lorentz force law. Now, if the momentum is increasing in the charges, it must come from somewhere because total momentum is conserved. And thus, this must correspond to a decrease of momentum in the field. So electric and magnetic fields not only carry energy, they carry momentum. Now, of course, we're very comfortable with that from our modern 20th century plus perspective of photons, thinking about photons as having energy and momentum. But it's a concept that goes back to Maxwell and the classical description of the electric and magnetic fields, and perhaps something you're less familiar with. What this says then is that the rate of change of momentum in the field, which I can think about as a momentum density in the field. So G here is the momentum density, just like we had energy density in the field given here. So we're going to try to figure out what that momentum density is today. But whatever that is, in this case, if it's increasing, it's because momentum is coming from the charges and being put into the field. So this is minus. Well, this is not quite correct, of course, because I have to have the flow. So I just, not quite correct, right? Let me go back to that and just say the following, that if rho minus rho plus or minus J over C cross D is equal to the rate of creation of momentum in the field per unit volume. Just looking at this equation. Okay, so we can look at this and we could use Maxwell's equations In the same way that we use Maxwell's equations here in the context of energy conservation to think about the rate at which work was done on the field is equal to minus the rate at which energy is created in the field as a quantity associated with the fields themselves, we can do the same thing here. So let's do this first. Let's just think about this for electrostatics, just to start. Okay? So in electrostatics, we have Coulomb's law. The force on a charge is Q times E, or that, right? That's the definition, in some sense, of the electric field. Now, rho is always equal, electrostatics or not, to del whatever the okay. Remember, this is the total E in this case, because here we're not looking at point charges, so this is the total E, including the external E and the E of rho itself. Because whatever del dot E is, it must be related to the local rho, if it's the total E. All right, so now we got to deal with a little bit of tensor algebra, which is everyone's favorite activity in the world. So let's look at the ith component of this force. It's the ith component of E, and then we have del dot E, which is that. Okay? So now let's do a famous aside over here. Let's look at the partial J EI EJ. That is equal to EI times partial J of EJ plus EJ partial I, no, partial J E sub I. Right? So, what can we say here? Well, I'm talking about electrostatics. What equation defines us to be talking about electrostatic field?
Del cross E equals 0.
Yes, thank you very much, Aaron. So if del cross E equals 0, that says that partial J of E sub I is the same thing as partial I E sub J, right? Because if I looked at the kth component of this, that's epsilon k ij di ej minus eg. Well, the kth component is this. Sorry. For the minus sign. So, the curl tells us I can do that. So, let's just remove that. This follows from that. And that tells me that this is equal to, I can take this guy over here and write it as Ej di Ej. But that is equal to 1/2 the partial of I Ej Ej. Right? Because from the product rule of differentiation. And so we learn the following. This is equal to 1/2 the partial of I of E squared. We can then say the following. The partial J of EI, EJ is equal to EI del dot E plus 1/2 partial I of the magnitude of E squared. And so we find the following. The force, the electric force in electrostatics, the thing that was Coulomb's law, can be expressed in a form that depends only on the electric field, not on the charge anymore. Because the charge is related to the field through Maxwell's equations. In this case, Gauss's law. And we get the following. This is equal to the integral over space, plugging in over there. We can solve this. We have del dot E is equal to this minus that. So let's look at the I component, because I don't want to get too many things at once, is equal to partial J EI EJ minus 1/2 partial I E squared, all over 4 pi. So, what we have is the following. Fi is equal to the integral over all space, partial I of a tensor that's called the Maxwell stress tensor. Actually, I'll call it TBJ, where Tij is equal to 1 over 4 pi EI EJ minus 1 over 8 pi delta IJ magnitude of E squared. This object is known as the Maxwell stress tensor. An object you may have heard of in the past. We'll explain what that term means in a moment. But written in vector notation, what we see is that the force on the charges is equal to an integral over all space of the divergence of this tensor, where this is equal to, if I write this out, partial I, and then I would have T, or partial J, T, that was the I component of this, TJI. Get too confused, so let me leave it as such. Is everyone clear that this is the same as this? This is the divergence of the tensor. The divergence of a tensor is a vector. The divergence of a vector was a scalar, because we're contracting one index. It has to be, because we're talking about momentum here. So momentum is a vector. So the flow of momentum is a tensor, because I could have these little vectors which are flowing in the same direction, or they could flow in this direction. So the question is, in what direction is momentum flowing relative to what direction is momentum pointing? There are two indices to worry about: the direction of flow and the direction in which the momentum is. And this is a little bit weird, because we're talking about momentum in the field. Of course, you got a particle, it's moving in one direction, we keep around one index. We talk about the momentum of the particle, it's got a vector. But the flux of momentum, or the flow of momentum, the local flow, is a tensor. calculated there. Okay, this is the most complicated form of Coulomb's law you have ever seen. In fact, it's going to get even more complicated in a moment. So, of course, we can use the Stokes, not the Stokes theorem, the Gauss theorem to relate the volume integral of the divergence to a surface integral. So that is dA n hat valued into the stress tensor. So, the stress tensor, what the heck is the stress tensor? Well, the stress tensor is an idea or concept that comes from continuum mechanics. Of course, you know, back in Maxwell's day, that was, that was the hottest thing, it was like the equivalent of quantum information. I mean, that was the hottest thing around. It was fluids and stress and continuum mechanics. That was the good stuff. And so the idea was that I could think about the force on charges as being related to the stress that the charges are feeling, which of course is the same thing as pressure, right? Because this has to have units of force per unit area. Because if I integrate over an area, I get the force. Force per unit area is pressure. So there is pressure being exerted as that is carried, this pressure exerted on the charges is the pressure coming from the electric field. So it says if I want to calculate what that pressure is, and of course it's a tensor, is the fact that you could push in one way, but it might go in another direction. It's not, it's got this tensor quality to it. So, how do we calculate that force? What it says is that we have to calculate the flux of this quantity out of the surface. The normal here from the Stokes theorem, Gauss's theorem, is this is the normal out of the surface. So, if I have some charges here, and I want to find out how much force is exerted on those charges, rho, one way I can calculate it, well, the way I really should calculate it is I find what the local electric field is, and I multiply that by the charge. But if I was really crazy, and today I'm just out of my mind, what I could do is I draw any surface I like through it, around it, sorry. I calculate there's some normal here, everywhere. Here a normal, there a normal. Everywhere a normal, normal. And I calculate the flux calculate the flux of n at dA out of that surface. And that flux is equal to the force acting on the charge. Okay? So that means that I can interpret minus n hat dA equals the rate at which momentum flows from field to charges through n hat dA. Because this is the force of the charges. We calculate that by calculating the flux out, but we want to know the force on it. So let's do an example. Here's the example. I've got two charges. Let's say they're both equal and opposite. I'm sorry, equal, period. Forget about the opposite part. They're separated by a distance d. What is the force on this charge? What's the force? Excellent. Let's calculate it in the hardest way absolutely possible you ever do this. Okay? So, we want to show that the force acting on this charge is equal to, well, I'm going to draw a volume, and that volume is going to be a hemisphere. The hemisphere with its equator halfway at the midpoint between these two charges. And I'm going to calculate the flux of the stress tensor out of this volume and show that it equals this. Okay? So, just like we had before, these are the field lines. In fact, at any point here, the electric field points along that distance, right? By the principle of superposition. So, we need to calculate that. I'm going to, in order to make my life simpler, I'm going to take the radius of this. I could do it otherwise, but I don't need to. I'm going to take this radius of this hemisphere to infinity. I mean, we could do it at a finite radius, and we would find that the contribution would be finite, and then there would be some finite over the disk part of this hemisphere. But it's much easier, because of the symmetries problem, to just look in the limit that r goes to infinity. So, everyone understand the geometry here? This is a hemisphere, so the bottom here is a disk, and then we got the dome, whatever you call it, the metrodome, and it goes off to infinity. All right, so we got to first of all ask ourselves, what is the stress tensor? Well, the stress tensor is equal to 1 over 4 pi E minus 1 over 8 pi, the identity tensor, E squared. Okay? So, we need to calculate, first of all, n hat times dA dotted into the tensor. So first of all, let's look at the case where I'm on the okay, so we have two cases to consider. We have n hat associated with the bottom of this, the disk, that's the bottom of this hemisphere, and we have this case. here as well. Now, first of all, what we notice here is that on the hemisphere, the dA scales like r squared, right? But what about the electric field, the tensor? How does that scale with r? Well, it falls off as we get far enough away, it falls off, the fields fall off like 1 over r squared, right? Because of the monopole. We got the square, so this goes like 1 over r to the 4th. Well, I say 4. Who knows what's inside that brain, but something little mice are running on dirt trails, I'm sure. As I said, I'm convinced. You all took that psychology experiment where the brain was cut in half, and the right side of the brain combed its hair, and the other one was like fighting it. I'm sure that's what I mean. My brain says one thing, but my hand does something else. There's inner conflict. Anyway, so what we see here is that on the hemisphere, this thing goes to scales like 1 over r squared, which goes to 0 as r goes to infinity. So that's why I can ignore the hemisphere contribution to this flux. And I can now just concentrate on the disk. Well, first thing we see here is that along the disk, E is perpendicular to the normal. So n hat dot E on the disk, if the disk is on the bisector between the two charges, n hat dot E is 0. Which means that this is equal to minus n hat over times E squared over 8 pi. Okay? Does this sign make sense? Is this the direction that you expect the force on this charge to be? What is the direction of the force acting on this charge? It's being repelled, junior high school physics. So, yes, it's minus n hat, so that's good. So at least we got the signs right, and now we just have to calculate. This is the electrostatic pressure. And we need to just integrate that pressure through the disk. So let's do it. What is the electric field on this bisector? What's the magnitude of E? So let's see. Here I am over here. The distance to this is d over 2. I'm at some point on the sphere S, on the disk, right? And this is sphere dr. Okay? So I have two charges. Each charge contributes the same field, but it's only, but one of them, the same magnitude of the field, but one of them has a field that's in this direction, and one of them has a field in that direction, and I only have to add the component that's along the disk because the other two can't. And this angle is theta, and this angle is theta. Okay? So, what is that? Well, the magnitude of E is equal to Q over script R squared times cosine theta, or the Z component. S component, yeah, that component along the S direction. Oh, did I screw that up? Oh, yeah, you're right, the sine theta. Sine theta, it's wrong in my notes. Thank you. Indeed it is. Yes, okay, thank you. And there are two of them, two charges. Each one contributes equal amounts. So that's the total E. This is the magnitude of E. It only has an S component when I add both of them together. So what is sine theta? So we have 2Q, what do we have here? S over R. Okay? So, and what is R? It's the square root of S squared plus D squared over 4. And then I have to take the cube of that. So that's the electric field. Got to plug that into here and then integrate. So the force is in the minus n hat direction. It's kind of 1 over 8 pi. Well, I got to 2q over 8 pi. Integral s over s squared plus d squared over 4 to the 3/2 power. And what am I integrating? dA, right? So what is my dA element on this disk for a fixed s?
2 pi s ds.
Right, so what I'm looking at, if I draw this now, here's the disk, looking at head on. I'm at some distance s over here. Everything is cylindrically symmetric about here. So my little element of area, dA, is naturally 2 pi s ds. Integrated, s goes from 0 to infinity. Okay?
You didn't square the field.
I didn't square the field. Thank you. Square the field. Thank you, Nick.
And 2K as well.
Let's look at something. Make sure I didn't make any other mistakes. What else did I screw up?
Oh, yeah.
2Q.
2Q.
The 2q has to be squared as well. That's good because the force better have a q squared in there. So I got a 4q. That cancels the 8 pi. 4q squared. Thank you. All right, let's double check. All good. This integral can be done. I'm not going to do it. I'm going to use the magic oven here and just pull it out, just like you and your child used to do. And write the answer over here. F equals minus n hat q squared times minus d squared plus 8s squared over 16 s squared plus d squared over 4 squared integrate from 0 to infinity equals minus n hat q squared over d squared. Yay. The hardest calculation you've ever done to calculate Coulomb's law. What kind of insanity is this? You would never do this. That's not the point of the Maxwell stress tensor. What the heck is the point of the Maxwell stress tensor then? Well, Maxwell stress tensor is important when we think about the dynamics case. And we want to think about the flow of momentum, particularly in waves. And moreover, you may have a t-shirt that has Einstein's equation on it for gravitation. And that source has a T mu nu in it. What the heck is T mu nu? Well, it's the stress tensor. We'll talk about the relativistic generalization of that. But the stress tensor in the electromagnetic field is a source of gravitational waves. So if you're ever going to study GR, which everybody should know something, you know, PhD in physics, you should know some GR. Know the stress tensor. So, let's talk about the dynamic case. Now, we can do the same thing for magnetostatics. I'll spare you that. That's, let's just say the general Maxwell stress tensor T, having both electric and magnetic and dynamic. It's just, it's just gonna be exactly the same form that we had in the static case. But now with the magnetic fields as well. Again, one could derive this part of it in the magnetostatic case. You would find it for doing exactly what we did with the Coulomb law, using the Lorentz force law part involving the currents, and we would get exactly the same expression, but now with B instead of B. Now we have both. All right? So, let's consider then the flux of this thing, or locally the divergence of this thing. Okay? Which is partial J T J I. This is the ith component of this. So, what do we got here? Well, we're going to have 1 over 4 pi d by dj ei ei. No, ei, ej ei. That's tji minus t and then the same thing for the magnetic field.
Wait, where's the minus one?
Plus. Thank you. BD. BJI. Minus half. E squared, which I call it. All right. So let's look at this. I think I got this backwards. This delta ij makes this a gi. Jj. I jj. All right. So now we do the same kind of tricks we did before, but now including the full Maxwell equations, not the ones for magneto or electrostatics. So let's look at this term first. This is equal to E sub I partial j E sub j, which is the divergence of E, plus E sub j partial j E sub I. Minus the derivative of this is twice, which cancels the half, ej di ej. So what we have here is equal to dj times dj ei minus di ej. Which is epsilon j I k, the kth component of the curl of E. This was 0 in the static case, but now it's not 0. So, this then, if we sum this with the epsilons, we're going to get the cross product between E and the curl of E. So, let's put it all together. I'll go back to the front board. And then the same thing would be true. So, skipping a little bit of algebra, you can try it yourself. The ith component, or let's just write it out like this. This is going to be E times the divergence of E.
That's the divergence. That's correct. Not the curl of the tensor.
No, this is this first term.
No, I know, I'm talking about your
Oh, that's divergence. Yes, thank you. Indeed. Okay. Then we're going to have plus E crossed into the curl of E. Plus B times the divergence of B. Plus B crossed into the curl of B. Let me just check on the signs here. The minus sign, epsilon. I have to switch this as a minus. Epsilon ijk. All right, so now we got Maxwell's equations. So far I just said this is the stress tensor, this is the divergence of the stress tensor. What's del dot B? Yay, something is 0. Del dot E is equal to, oh, this is all over 4 pi, isn't it? Yeah. 1 over 4 pi times everything. What's del dot E? 4 pi rho. What's del cross B? Quick. It's got a dt in it. What else has it got? It's got a minus sign.
Minus whatever it is.
Minus 1 over C, yay. Del cross B equals 4 pi j over C plus 1 over C d dt. So, what we have is the divergence of the Maxwell stress tensor equals rho times E plus J over C cross B. That's this term. Then we got other terms here. We have plus 1 over 4 pi c. That's not an epsilon, it's a c. E crossed into dv dt. And then there should have something screwed up here. What did I do wrong? Oh no, that's right. Yay, that's good. Which says, so this is equal to d by dt of E cross B. So, what do we have here? Well, luckily, I didn't get too far because I still have on the board the important equation that we started this whole discussion with. Minus the Lorentz force density is the rate at which momentum is created in the field. So this is equal to a vector, so rate at which momentum, a vector quantity, is created in the field, right? Per unit volume. Oh, it's minus the rate. Thank you, Aaron. So now we can solve.
Which is which?
The negative is the rate,
This is the rate of creation.
right? The positive one is the rate at which momentum is absorbed from the field and put into the charges. That is the rate at which momentum changes in the charges, which is the force on the charges.
Minus R is not the rate of creation.
No. The rate of creation is equal to minus rho. The rate of creation is minus rho E minus 1 over C J cross B. So now we can solve this equation, or at least put it in a form that is in the form of a conservation law. It says the following. d by dt of G is equal to del dot minus T plus R momentum. This is the equation of conservation of momentum. Where G is equal to E cross B over 4 pi C, which is the Poynting vector divided by C squared. And G is the momentum in the electromagnetic field per unit volume. what does this equation say? It says that the local density of momentum in the field changes. It can change if that momentum is imparted to or taken from the charges, or if momentum flows. And the direction of the flow is related to minus t. I mean, that's what we saw before, right? The momentum flowing into the surface was minus t. So the stress tensor is related to the flux density of momentum. This is like the current of momentum. Momentum is a vector. The direction of flow need not be in the same direction as the direction of momentum, which is why it's got this devilish double arrow head on it. The divergence of that is a vector. G is the momentum density. It's the amount of momentum in the electromagnetic field per unit volume, such that if I were to integrate this over a volume, that would tell me how much momentum is contained in the field. So electric and magnetic fields not only contain energy, they contain momentum. I mean, in some sense, we could think about this as a bookkeeping exercise. I mean, you know, when you take freshman physics, you say there's two kinds of energy. There's kinetic energy and potential energy, right? When you raise up the mass in the gravitational field, we say now it has a different kind of energy, it has potential energy. But, well, really, it's not the mass that has the energy, it's the gravitational field that has the energy now. And then when I drop it, then it takes it from, you know, see or whatever. Then it takes it from the gravitational field and, you know, shatters it. Similarly, when we're talking about momentum in the field, well, what we're saying is that if momentum is taken from the charges, or given to the charges, then momentum went somewhere, or came from somewhere. And that somewhere, in this case, since we're talking about momentum coming from the Lorentz force, which is the starting point of the whole discussion, that momentum density is here. And when you quantize the field, this is what becomes the momentum operator in quantum electrodynamics, which for a bunch of plane waves would be h bar omega times k. Or h bar k, sorry, in the k acceleration. H bar omega energy, or k is the momentum. You'll have a nice exercise for that. Maybe angular momentum, that's much more fun. We'll talk about that briefly next time. Yes?
Try to just keep track of the minus sign. Should there maybe be one to the left of the del in the nice box to create?
It's del minus t.
I know, I think we need another one. Maybe I'm just being stupid.
It's probably me who made a mistake. No, this is equal to, so this, no, I think this is actually right. This is equal to minus r. Right? You buy that?
Yeah.
This is equal to so yeah, there's something funky going on in there. I'll double check it and get it right in my notes. Thank you. But this expression is correct, I'm sure.
Okay.
My derivation thereof, question. Okay. I'll double check it. Okay, guys. I will distribute the